Chemistry 6 markers today. They're kind of my favourite because you can use the Smart G method on those. So we're going to do a bit of that. Not much more to say, really. So I split it up again into paper 1 and paper 2. Most of the things, in fact, I think all of them are the same for Excel and AQA. Only difference that we've kind of noticed is that they like to put 4 markers in at Excel with some of this in as well. So they're not always 6 markers. Normally they throw a few 4 markers in there with the same kind of idea, but it's the same kind of method to do it anyway. Just a fewer marks available. So having looked through them all, most questions that are used for 6 marks questions are either method questions. So how do you do a particular experiment? A lot of them seem to have a wrong method sometimes. They tell you, look, they've said this, what have they done wrong? So they're based around your required practicals. Calculation questions, I like to do those and evaluate based on some data that they've given you. So I've used 3 questions for this section 1. I've used a planning, a calculation, and an evaluate one, comparing bonding. So we'll start with the first one. Okay. So a student plans a method to prepare pure crystals of copper sulfate. So that is one of the required practicals. The student's method is add 1 spatula of calcium carbonate. So this is where I like to kind of underline what they've been using. Calcium carbonate to dilute hydrochloric acid in a beaker. When the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. The method contains several errors and does not produce copper sulfate crystals. So that is the thing we're trying to get. Explain the improvements the student should make to the method so that pure crystals of copper sulfate are produced. So, Connor, what is the first thing you notice? If we're making copper sulfate, what is the first error that they have done?
There's no mention of a copper sulfate.
Yeah, it says calcium, doesn't it? So calcium won't lead to making any kind of copper compound, so that's no good whatsoever. And what about you, Louis? Anything else you've spotted that's wrong?
I'm not too sure. Chemistry is one of my weak points.
Fair one. Well, hopefully we'll put that right. So 1, calcium should be copper. And I suppose it still could be carbonate, couldn't it? That's not a problem. We just have to swap it for copper. What about you, Amina? Have you spotted anything?
It says heat the solution with a Bunsen burner till all liquid is gone.
Yeah.
You don't evaporate all the liquid. You have to leave it to cool.
Yeah.
Otherwise, there'd be no crystals formed.
So probably no Bunsen burner. But instead, maybe something like a water bath, yeah? Now, the thing I've spotted, hydrochloric will make a chloride, won't it? And because we're making a sulfate, that isn't going to work. So what acid might we use instead, Louis? Here's your chance.
Sulfuric acid.
Yeah, that sounds good. So all I think that this has actually helped us do is it has helped us kind of focus exactly on what chemicals to use, okay? Instead of just writing a load of old rubbish. So that was kind of nice of them in that question to do that. Now, this is where I would go to using this method, this Smart G method. Now, some experiments will have all these things in, some will not have all of them in. And it's normally the 2 down at the bottom. So then not in all exps. I'll just put exps. State number, that can be state number or chemicals involved. So if we're just having to think about what chemicals are involved, we've just gone through that. So we will be using copper carbonate. And I suppose we could, if we really wanted to, use copper oxide, and that's the one that most people use. So this is the more common. And the difference that makes is that if you use copper oxide, you have to add it, stir it, add it, stir it, and the copper oxide will disappear. It's a black solid. And when there's black solid left, that's when you know you're in excess. Copper carbonate starts off green, and the way you know you're in excess with that one is that the fizzing stops. So depending on which one you choose will determine what you write in your method. Measure properly. So I always think measure, method. So what am I going to do for my measuring and method? So I would probably want, say, 50 centimeter cubed of, oh, I forgot one of my chemicals, didn't I? Sulfuric acid. You know something? I got pulled up in a job I was doing by the head teacher. Said, you're still spelling sulfuric acid with a PH. It changed in 1990 something or other. But I just don't like the American spelling with the F, but because that's what's in the exam, that's what I use now. So I think we've got all the chemicals now. So we'd want 50 centimeter cubed of sulfuric acid. What bit of equipment might we use to measure that, Connor?
Measuring cylinder.
Yeah, always go measuring cylinder, because you will get pulled up if you put something like measuring jug, which a lot of people write, and I don't even know what they mean. Do they mean measuring cylinder? They just can't remember the word. Or do they mean beaker? Because a beaker is really inaccurate in terms of measuring. In terms of putting our solid in, Louis, are we measuring that, or what would we do?
Would you weigh it?
You might weigh it. You don't actually know, though, how much you're going to need, do you? So there's no real advantage in weighing it. What do you normally do, Amina?
Do you add it to a beaker?
Yeah, so you
Or
would.
you add excess coppers?
Yeah, so you'd put that in a beaker. And just to be extra safe, I'd put 100 centimeter cubed. You want it bigger than what you've measured out. You don't want it up to the brim. And then we're going to add the, shall we do copper oxide? Because it's kind of the more, no, we'll do copper carbonate because it's a bit different. Copper carbonate with a spatula, I'd have thought, a spatula at a time. And then how do we know when to stop with that one? Louis, how would we know when to stop?
Is it when it gets to 50 centimeters cubed on the measuring cylinder?
I'm on about adding the stuff in now. How do we know when to stop adding it?
I'm still not sure.
Okay, what do you think, Connor?
Until it doesn't dissolve anymore.
Yeah, there's a big giveaway though, isn't there? And it's this one up here. It's when the fizzing stops. So until the fizzing stops. And just to be sure, because there might be some fizzing you can't see. So you put and solid copper carbonate remains. So once you're at that point, what we're doing next? I should have left a bit more room for these method things. What would we do next then, Amina? Once we've added our excess,
Would you filter it?
yeah. So that's like number one. Number two, we're going to filter it. So this is when we might want to just mention what we use. So it is kind of moving into the apparatus. Filter it. So obviously that's with filter paper, filter funnel. And then once you've filtered it, take the solution. And what do we do then with the solution, Louis?
I'm still not sure. I'm really lost.
All right, okay. So what I might do then for the apparatus bit, instead of writing out all the apparatus out, I'm going to kind of do a diagram. So what we've got is we've got a beaker. We've measured out our acid. We've put it in there. So now we've got the acid, and then spatula. We're going to add our green stuff in there, yeah. You might want to stir, and eventually you'll get to a point where you've got this blue solution, because what you'll have made is copper sulfate, and you'll have some green powder left in the bottom. So at that point, we've filtered it. So it would filter into a conical. We'd have our filter paper in there. And what we should hopefully have is some green stuff left in there and a nice solution of copper sulfate. And then finally, we put it into an evaporating basin. And the best way of doing it is on a water bath. So you can heat up the water any way you like, really. You could heat it up with like a hot plate, or you could use a Bunsen. It doesn't matter, because what you're doing is you're just heating it, and the steam heats up your liquid. The water evaporates. And then what you can do is you can leave your evaporating basin to dry out with the kind of mushy crystals left. Leave it for a few days somewhere warm, and then you've got your crystals. So I don't feel the need to label all the apparatus there, because the drawings are decent enough to work it out. So that would be our apparatus, all that stuff there. So the result, what we're looking for, well, we're not really looking for a result, are we? Other than kind of looking to see if there's green stuff left over. So we might just put that. That's in step one, in it. Green powder left over. And then, excuse me, and then in number 2, we'll be looking for a blue solution. So I normally just use the R for all the things I'm looking for at each stage for it to be finished, because this is a multi-step thing. There's like a few things to look at. So blue solution, and finally we'd have blue crystals. Another way that they talk about drying them off as well, that they allow, is to use like, what do they call this stuff? Told you there'd be somebody lawnmower in, didn't I? What do they call it? Like paper towel. And you can dry the crystals off with a paper towel if you want. Yeah, the problem I've got up here is that I'm warm because the sun's out, but I need the window open so I get noise. Right, test again. Do I need to test this again? Well, if I was looking for numbers, if I'd done something that involved exact numbers, I might test it again to get an average. So this is normally for getting averages, but it's not needed in this. And then go again. This, if you were doing this one to go again and compare something, you might use other compounds, but that's not what we're doing in this one. So we have to just put that into a an answer, don't we then, really? So that would probably look like, what would you say? So explain the improvement. So we could say use copper carbonate instead of calcium carbonate. Use sulfuric acid because hydrochloric does not make sulfate. So we've answered the bit about the improvements, and then we'll include the bit about the Bunsen burner later on. So we just have to write it out. So it was measure 50 cm cubed of H2SO4, so that's sulfuric acid, using a measuring cylinder and put it in the beaker. And there's nothing stopping you from just scrolling down. Obviously, you don't scroll in an exam, but what you do is you look at where you've written this. So this you'd probably write, you know, on the pages where you've just got blank at the back, just write it on there. So measure it out, put it in the beaker. Number 2, we're going to add the copper carbonate, a spatula at a time, and stir. Repeat until there is no more fizzing and green powder remains. Looks like I need another page. So number 3, we're going to then filter using filter, paper, and funnel, and collect. Now, you might not know this word, and if you don't, it's fine. You can just put liquid, but collect the filtrate in a conical flask. So we're just making sure that we're mentioning all the equipment as we go. Transfer the copper sulfate solution to an evaporating basin. And then we're going to heat it with the water bath. Heat on a water bath. Does anyone know what we're heating it until happens? What do we normally say? Just unmute yourself if you know. Heat it until what happens?
It boils.
It boils? What do you think, Amina?
I think this is completely wrong, but is it equilibrium?
Equilibrium. Do you want to have a go, Connor?
I'm not sure.
I would just say it. Heat on a water bath until you can see crystals. Now, Amina, you should be an expert on this. Do you know why? Because the other day when we talked about this, we said if you heat up copper sulfate really strongly, all the water that is attached to the copper sulfate will go as well. You'll end up with a white powder of anhydrous copper sulfate. So that's what we're avoiding. So if we do it until we see the crystals, then we should be okay. And then leave it to dry in a warm place, or pat dry with a paper towel. Now, I'm interested to know how many that is because I have not looked at the mark scheme for that, so we will find out now. Where are we? Mark scheme. nice and small. I love to be able to zoom in. Right. So use sulfuric acid and not hydrochloric acid. Have we said that? Yes, we have. What else have we got? Uses copper carbonate or oxide. Yep. Add solid until solid remains or no more reacts. So there's no mention of the fizzing, but that would also be an indicator of it. I think that's fair. Filter to remove excess or unreacted. So I think that's maybe something to add in. So what was the word they used? To remove excess. So that's just something we missed out. I don't know if it'd be worth a mark or not, but it's worth putting in. Heat gently or leave until crystals appear or crystallize. So that is the kind of all that. And then the way you determine whether it's 6 marks or not. No relevant content. Well, we've got loads of relevant content. Points are identified and stated simply. I think we're better than that. Relevant points and reasons. We did give reasons because we said hydrochloric wouldn't give a sulfate, for example. And if we look at level 3, you've given it in detail, logically linked to form a clear account. So there's no reason why that wouldn't get a full 6. But I think that is important. So I'll put a star next to it to remove the excess. What do we think about that then? What do you think, Connor?
I think that's pretty good, that, to be fair.
Yeah, it helps, doesn't it, though, knowing to talk about your chemicals, how you're going to measure it, what your method is, and then the right equipment. There's nothing wrong at all with drawing a diagram somewhere as well, because I have seen it in mark schemes for particular questions. Not this one, obviously, but for some of them, it does say credit a diagram if it's labeled. So if you do a label diagram, I would do both. I'd do, because they normally have like a little white gap somewhere. They haven't on that one, but you'd have a little white gap. You do a diagram, and then looking at that diagram helps you, and you can just tick it off as you go, just ticking off all the bits and bobs that you've used and making sure that they're in your method. So if you've taken the effort to do a diagram, you might as well get the marks for it, hadn't you, in your method? So, yeah. We'll move on to another one then. Slightly quicker, this one. I'm interested to know just where we're at with these kind of things, because the idea is not to teach it fully, but it is sometimes a topic that people struggle on. So what we have got for this one is 108 grams. So I'm underlining 108 because it's going to be important. 1.21 kilograms of copper, right? Copper chloride. So what is the first thing we should do if we've got grams in one and kilograms in another? What do we think, Louis?
You convert it to one or the other, so I usually convert it into grams.
Yeah, that's dead right. So 1,210 grams to produce copper. The equation is now. Any ideas, Connor, shall we go with, on how we're going to just approach this, calculating the mass of the copper produced? What are you thinking?
I'm not too sure on this one either.
You know, I've put a thing on TikTok today saying I'm going to do one of these live on there later, and this topic comes up a lot. I think a lot of people struggle with it, so you're not on your own. This all revolves around the numbers in front of everything, okay? Now, I'll do my best to help you understand what it all means and the way I kind of think of it, because I have struggled with this forever, basically. Even when I was doing A-level, I struggled with it, and I don't think that my teacher particularly helped me through it. I maybe got it right, I've no idea, but this way seems to help me quite a lot. So what we've got is we've got a ratio of things here. So if we just put 2 there, we need 2 aluminiums. They would react with 3 copper chlorides, and they would give 3 coppers and 2 aluminium chlorides, right? So it's a ratio 2 to 3 to 3 to 2. Now, you know that just from looking at the reactant side. So if we split that, you need more copper chloride than you need aluminium, don't you? You need 3 divided by 2 times as much. So you always just use the numbers in the ratios help you. So from that to that, it's 3/2 times as much. If you want to know what the ratio of the products is, that to that, it's the other way around. You know you're getting less. 3 coppers gives you 2 AlCl3, so you're getting less. So it's 2/3. You'd have to times it by, if you knew that one. So we have to look and see what are the bits we know. So we have, it says, first of all, determine the limiting reactant. And then we've got all the atomic masses. Now, we know that you need 2 to react with 3. So this means you need 2 moles of it to react with 3 moles. So we need to work out how many moles we've got. So I would attack this by working out the moles of Al. So I'll do that first. And then I'd work out the moles of CuCl2. So the moles of Al, we have got 108 grams of it. So it's using the equation mass over MR. So it's 108 grams divided by 27 grams per mole. What that means is if you've got 27 grams, you've got 1 mole. So if you've got your calculator there with you now, work that out. I will be doing the same. Right, Amina, what have we got?
I've got 4.
Yep. Everyone else got 4?
One thing I'm a bit confused on is where's the 108 from?
The 108 came from up there.
Okay.
Yep. Louis, yeah? You had your hand up.
Oh no, that was like a misclick.
Okay, did you get 4 then as well?
Yeah.
Okay, so we've got 4 moles. Now, it might be worth just writing this on somewhere just so we know what we've got, okay? Now we're going to look at the moles of copper chloride. Now, it has given us the MR. We don't have to work it out, so that's nice. So moles of CuCl2. Same again, mass over MR. So the mass of it is 1,210 that we converted earlier, divided by 134.5 grams per mole. So work that one out and come back to me. Okay, Connor, did you get that one?
I don't think my calculator's right, if I'm being honest.
Go on, just read it out.
I got like 8.9962.
Yep, that's right. With these kind of ones, I like to leave 3 decimal places just so that when I give my answer, I've not made any rounding errors. So we have got 4 to 8.996. Now, it's nice in a way, that one, because all that's happened, if I zoom in, all that's happened is that's doubled, okay? But this one, if it had a doubled, would have been 6, right? But we've got 8.996. So we've actually got 2.996 moles more than we need. And because we've got more than we need, that's the one that's in XS. So there's more copper chloride than what we need, okay? Who was that? Amina, yes.
Oh, sorry again, but how did you get 2.996? Did you divide them?
I've just taken the 6 moles that it should have been reacting with. So 2 to 3 is the same as 4 to 6, isn't it?
Yeah.
And because we've got 8.996, I did 8.996, take away 6, and that's left with 2.996 moles more than what we actually need.
Oh, okay.
Does that make
Thank
sense?
you. Yeah.
Yeah. Good to ask questions, though, because if you don't, you'd be sat there not knowing what's going on. So we've determined the limiting reactant to be the aluminium. So I suppose we better write that. Aluminium is the limiting reactant. That's a funny way of writing that. Limiting. Because we have a ratio of 2 to 3. We have 4 moles of Al. So only need 6 moles of CuCl2. We have, oops, that's a funny. We have 8.996. Therefore, it, and I won't put it because it's the bad word, isn't it? CuCl2 is in excess and limited by the moles of Al. So we've done that bit right. So what we've got to do now, calculate the maximum mass of copper. Now, again, what you'll see is copper, if you start off with 2 moles of that, you'll get 3 moles of copper. And we already have the number of moles of Al, don't we, there? So 2 would have given us 3. I'll just do an extra page here. So 2 moles of Al would give us 3 moles of Cu. We've got 4 moles of Al, so that would give us 6 moles of copper, wouldn't it? Yeah. So this is time to just use moles equals mass over MR. So we go moles equals mass divided by MR. We need 6 moles of copper, so this is for Cu. We've got 6 moles. We don't know the mass, but we do have an MR, and the MR was given up here, 63.5 grams per mole. So if you rearrange that, you've got mass equals 6 moles times by 63.5 grams per mole. And if you work that out, I don't know what you get. Let's find out. What have we got? Connor, 6 times 63.5.
Oh, I was still writing stuff down. I didn't get time to do it.
Okay. Do you get time, Louis? Still with us, Louis?
I got 24,193.5.
Did you do? You haven't done that in your head, have you? Because if you do 6 times 63.5, what you can do is you can just round it to 60 in your head. 6 times 60, 120, 240, 360. So it should be around 360. It should be a bit bigger. If you get 20,000 something or other, you know that you've done it wrong.
Oh, I think you put equals twice.
Yeah, so this is what I say. Try and do it in your head to give yourself a bit of a what you're aiming for. And then when you get your answer on your calculator, you'll know if you're in the right ballpark. So, Amina, what did you get?
381.
381. So that's how many moles of, mass of Cu, 381 grams. So we can just put these in here. So 381, and we said the limiting reactant is aluminium. So if we have a look on the mark scheme, what have we got? We've got two methods. Moles of Al, well, we did that. We got the 8.996, we got that. 4 moles gives 6, yeah. I don't know what that other bit is, but we've got that bit right. Therefore, aluminium is limiting, yeah. Mass of that, yeah. So we've got all those parts, and you've got your 6 marks. But that is tough, isn't it? That's not a normal, easy kind of question. But then again, it were a number 7. Number 7's, I don't know, is it worth doing the 6 markers at the start, using your time on those wisely? Or is it worth doing the first bits fast and then just spending lots of time on these? You need to think of your tactic, though, because you can't do these in 2 minutes. You need to have a good think. Right. I don't think if I do this, I'll have time to do any paper 2 ones, so I won't do it. But I'll just do a kind of a rough what I would do. So compare the structure and bonding. So we'd be looking at the sodium chloride and the oxygen. First thing we see on the sodium chloride is that we've got charged bits on there, positives and negatives. And on the oxygen, we don't. We know that sodium chloride, we've got a metal and a non-metal, so that makes it ionic. Oxygen, it's 2 non-metals, so it's covalent. Both would have full shells of electrons. Both would have strong bonds. If we look at differences, one's got 2 elements, the other one's got 1. One's in a giant ionic lattice, the other one's a simple covalent molecule. The ionic one involves transfer of electrons. Oxygen involves sharing electrons. And then in terms of strength, the strength of the bonds is strong in both, actually, but if you were thinking about melting points, boiling points, sodium chloride would be really high, just due to how big the lattice is and how many of those forces you have to overcome. Whereas oxygen, it's only got that force between the 2 oxygens, and the forces between the molecules is really low. So that means you don't need a lot of energy to overcome them. So if you bang all that in an answer, you'd be very close to getting 6 marks, because it's basically a list one. Couple of things that are the same, more than a couple that are different. So that's the paper 1 stuff. Same again, paper 2, they just do the same kind of thing. I'm going to take a little vote on which one you want to do, because I think they will take a while. So we've got a planning one about chromatography. So if you want to go through the planning stuff again, I can do that. We've got a describe one, which is about the atmosphere, the formation of the atmosphere. And we've got one about carbon footprint, and it's about cars, which is actually quite a difficult one. So what do you fancy, Amina, out of those 3?
I actually don't mind, but maybe chromatography.
Yeah, what do you think, Connor?
Yeah, probably the chromatographer.
Louis?
Atmosphere.
Right, I'll try and fit them both in. Right, chromatography 1. Black ink is a mixture of several colours. Plan an experiment using paper chromatography to separate the colours in black ink. Identify the colours from their RF values. Okay, so if we're thinking about kind of like the Smart G again, what do we need? Well, we need some water, don't we? We need the ink. We need some paper, chromatography paper. Probably need a pencil as well. which kind of is part of the chemical, but not really. Method. So we've got to mention a couple of things. Don't put the ink spot below the waterline. And start line in pencil. And if you remember, it kind of looks like this, doesn't it? So you'd have your water there. You'd probably have something like a splint or something holding it there. You might want to put a lid on it. That's the most wobbly lid I've ever drawn, but a lid. Your start line, have I got a grey? No, I'll do the start line in like yellow or something. And then your black spot needs to sit above there, doesn't it? And when you've done, you should end up with your no dot anymore because the dot's moved. Still have your start line. And whatever colours are in it, I don't know what's in it. We've no idea, have we? But whatever colours are in it, maybe it's like a purple. Normally get like a streaky kind of purple, don't you? Maybe it's a blue mixed together. And what you need to do is mark on where your solvent front is. So this is all part of the method. So solvent front, you mark on there. And then what you've got to do is you have got to measure the distance the solvent actually moved. So that's the total distance. So for example, it might be 8.2 centimeters. And then you go to the center of your smudge to work out the RF value. So RF of blue. So say that was 6.3 centimeters. It's just a ratio. So it's 6.3 centimeters divided by 8.2 centimeters. So if we just quickly work that out, you don't need to do this one. This is for me, this 6.3 divided by 8.2, 0.77. And there's no units because centimeters cancel with centimeters. So that's kind of how you would do it. Obviously, we need a ruler in there as well. Did we mention that? So apparatus, ruler, beaker, lid, important as well. And then we'd probably have to explain how to do the result. So we'll explain that. So I'll go through all that now. So number one, and there's no problem in doing this as a list. One, take your chromatography paper and draw a start line with a ruler in pencil. Now, because I've done so many of these and I kind of know what mark schemes like to have a go at, they'll want to know why you've done it in pencil. So you would say, because pencil doesn't run. So next thing is place black. Is it black? Black ink dot on start line. 3, fill Louis.
Instead of saying because pencil doesn't run, can't you just say pencil's insoluble?
Yeah, you could also say because pen does run. They call that ORA or reverse argument. So anything like that's fine. So fill beaker with water so that it just touches the paper. And then again, this is why we're doing that. So this stops the ink running into the water, or as you might put it, dissolving into the water is probably better. It's good to pick me up on that. And ensures it moves up the paper. So at this point, we think it will have split into some colours, don't we? So we need to mark where the solvent gets to. Again, with pencil, you can never do this right, because obviously writing on something wet with a pencil is never very good, but you have to do your best. So mark where the solvent gets to with pencil, and measure the distance. From this line to the start line. Then we've got to measure distance of dot. What did it say? From center of one of the color spots to the start line. So once we've done that, we have to work out RF value. So I just use the equation RF equals distance spot moved divided by distance solvent moved. Amina.
You know, for point 4, when you said the solvent,
Yeah.
are they two separate lines? So is the solvent line at the top?
Yes, so the solvent line is where we marked it there, solvent front.
Oh, so is that okay?
Solvent front or solvent line, whatever you want to call it. It's actually called a solvent front, but solvent line's fine.
Okay.
Diagram's doing a lot of heavy lifting for us here, though, isn't it? If you've got that written down on your paper next year, it's like on this exam where I've got it, there's a load of gap there to be drawing. So you could draw it there and then write about it. So once we've done that, I suppose what we need to do then is we need to compare the RF value. So this is the results bit, isn't it? Compare the RF value to known RF values. Because the key here is every chemical should have its own specific RF.
Oh my god, you just wrote 6-7.
You what? So compare the RF volume to known RF values. So they should all have their own RF values. And then you identify the chemical. And then the last bit of this, which is the G, the go again, repeat for the other ink spots that moved. And I think, can you do any more for that? What are we thinking? Is there any more than that? Let's have a look then. So late to the production of a valid outcome. I think we're in 5-6 territory. So we've drawn this pencil line. We did say that near the edge. Maybe I didn't say near the bottom edge. What did I write? So might be good to put in near the bottom edge. Like I say, you can miss something out like that, still get all the others. Put a small dot of black ink on, put a small volume of water. So we've done that. So that it just touches the paper, yeah. Place the chromoscopic paper in the solvent. Should rise above, support the paper, put a lid on. So why did we draw it and not write it? So put lid on, support the paper. Leave it to run. Mark the position of the solvent front. So mark where it gets to, yeah. Remove the beaker and leave it to dry. We didn't say that, did we? So leave to dry. You can do these wet, so I don't know, see why that matters. Determine the RF values. Measure the distance, calculate it, compare. So we got all those things. Measure the solvent front there. We did that. Compare it to known values. So what we're saying, is that 5? Is that 6? Couple of bits missing, but indicative content. It doesn't say all of it has to be there. It says, would it lead to a valid outcome? Well, it would. So I can't see why that wouldn't be a 6. But just to make sure, you probably would want to put those in. So the near the bottom edge bit, it's, you know, you want to give the examiner the best opportunity to give you full marks, don't you? You don't want them doing what we're doing, going, is it 5 or 6? But how easy is it just to miss out something that we actually spoke about? Put the lid on, support the paper. So that was as lid, and that was as support, wasn't it? Right, I think we've got maybe just enough time to either go through this one verbally or just maybe write a few bits. In fact, I might ask you to tell me a few bits. So we've got describe the processes that have caused the main changes in the percentage of carbon dioxide in the Earth's atmosphere over the last 4.6 billion years. So just put your hand up then if you've got some thoughts on that, if you've got anything that you think we would. Who was that one? Louis, yes.
All right. So essentially, Earth's early atmosphere was made of the most part carbon dioxide.
Yeah.
Very little nitrogen and very little oxygen compared to today, where it's about 71% nitrogen. No, it's 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, and trace amounts of small gases.
Now, you're at a good position there, aren't you? Because you've got all the kind of data just reeling off your brain. But if you notice what it says describe the processes. So we have to describe why it was mainly CO2 in the early atmosphere. Amina.
Would you link the processes to the carbon cycle or carbon capture?
I would go through them in order and give, it might be a reason from the carbon cycle, but it needs to be the right one, doesn't it? Because not all parts of the carbon cycle were there back 4.6 billion years ago. Louis.
So essentially, like relating to nitrogen, nitrogen's like typically a more unreactive gas.
Yeah.
And it mainly needs like high temperatures and a catalyst to react. So is that the reason why there's majority nitrogen in our atmosphere today?
Yeah, it's just really unreactive. So that's generally why it stayed around. It's not really a case of there being so much of it. It's just that the other things are used. So actually, in relation to the thing that's not being used, it's a high percentage, if that makes sense. Let's just focus back on this because it does say the main changes in percentage of carbon dioxide. So nitrogen chat is great, but it's not going to get any marks. So why was that early atmosphere mainly CO2? What was causing it? Help me out. Connor, where was it coming from?
Volcanic.
Yep. So volcanic activity. Now, unfortunately, I think we're going to have to put dates on this. So I'm going to put like the first billion years. And that's pretty much it for that bit. And then we're going for kind of the next section. So what's happening in this next bit that's causing CO2 to change? First of all, is it going up or down? What do we think? What do you think, Louis? Does it go up even more? Does it start going down? Yeah.
It starts going down.
Yeah. So I'll just kind of do it quick, free, short answer. CO2 goes down. Why is that? Amina, why is it going down?
I'm not sure.
Okay. Who's that? Louis, yeah.
Is it because the planet's cooling down?
Yeah, so I'll definitely include that. Planet is cooling. What does that mean for the water vapor?
Does it mean that the water vapor can turn into a liquid in quick form?
Yeah.
And because the ocean is like a huge part of like carbon, it's a huge carbon sink. So
Yeah.
the majority of the carbon dioxide gets dissolved into the oceans.
Yeah, so there's a lot dissolving in the ocean, and a lot of the things that in the ocean for the next however many billions of years, you would get carbonate deposits as well. So you get carbonate deposits, eventually turning into sedimentary rocks. So that's another thing that gets rid of it. So that's probably, what is that, 4.6 to around about 2.7 billion years. Right. What I'll do is I'll just wrap this up now. So what we've got now again is I'll just put plants. So you've got a rough idea. I'm sure you could be able to work out plants. And then we've got for like most recent, so 200 years ago to now, we've got Industrial Revolution. We've got increase in population, so we get more human activity, don't we? Is going up. And then we've also got the burning of fossil fuels. I've missed out the plants bit because most people tend to know what that did. Plants make CO2 go down, don't they? These are all making CO2 go up. Right. Are there any questions that we've left unanswered today that we want to ask before we go? Amina?
No, nothing.
Okay. Connor?
No, I think it's all been covered.
Yeah. Louis?
I believe today's session was very good, and I believe
Good stuff. I would recommend having a go at this other one, though, in your own time when I send it to you, because there's some rather fancy maths in there. So if you do have a go at it and you can't quite understand it, I will maybe write you a little page on how it all works, because it can be confusing. But otherwise, thank you all for joining in, and I'm glad you've got something good out of there again today. And thanks all your parents and whoever else who's sent nice messages as well. Amina.